Hello, this is our presentation on flow past immersed objects and packed fluidized beds by Hunter Black, Ella Page, Shane O'Connor, and Sabrina Campos. The first slide is about drag coefficients for flow past immersed objects. The flows of fluids can be found in many chemical processing and engineering applications. The force exerted by the fluid on the solid in the flow direction is called wall drag. Wall drag can also be known as skin drag. There is another additional form of drag called form drag, which is caused from significant additional frictional losses when the fluid has to change directions around the solid body. In the flow around a solid object, there is a point at the front of the body that has zero velocity. This is known as the stagnation point. The stagnation point is where the velocity layer is the same as the fluid velocity adjacent to it. There is a point of separation behind the fluid, which is caused from deceleration and acceleration of the fluid. This causes eddies and turbulent wake to occur, as you can see in figure B and C of the photo on this slide. The point of separation depends on many factors, including the shape of the particle and the Reynolds number. Form drag can be minimized by streamlining the solid body in order to reduce the wake behind. Streamlining the solid body is a principle which is used in aerodynamics for planes and many other flow processes in chemical processing. Our next slide covers drag coefficients more in depth. The shape of the solid body is very important for determining the total drag force applied. If, as you can see in the GIF here, if there's a larger front surface, there's going to be a larger turbulent wake behind, which has a higher drag coefficient. The drag coefficient is the total drag force per unit area divided by the dynamic pressure. You can see that in the equations on the slide. FD is the total drag force, AP is the surface area, rho is the density, and V naught is the free stream velocity in these calculations. The table on the left of this slide includes some drag coefficients for common geometries found. Notice that the more streamlined the body, the less drag that would be observed for an object of the same area. You can rearrange this drag coefficient equation to get an equation to calculate the total drag force. With various physical properties such as the density and viscosity, you can calculate the Reynolds number too, which is very important for determining if the flow is laminar or turbulent in your flow boundary layer. Our next slide covers flow past spheres, long cylinders, and disks. The theoretical Stokes law equation correlated with the experimental drag force for spheres in the laminar region when the Reynolds number is less than 1. You can combine the Stokes law with the drag force equation from the last slide to achieve a formula for the spherical drag coefficient, which is 24 over the Reynolds number. When the Reynolds number for flow around a sphere or cylinder exceeds the applicable Stokes law range, wake is formed behind the sphere from separation occurring. At a Reynolds number of 300,000, there's a drop in the drag coefficient due to the boundary layer becoming turbulent. Between a Reynolds number of 1,000 and 200,000, the Reynolds number is a constant, but different for shapes. In this range, the Reynolds number for a sphere is approximately 0.44. Drag coefficients are constant again above a Reynolds number of 500,000. They can be approximated as 0.13 for a sphere, 1.2 for a disk, and 0.33 for a cylinder. The table on this slide has a graph that you are able to read off the drag coefficients for spheres, cylinders, and disks once you have the Reynolds number calculated. Fluid flow past arrangements of cylinders and tubes occurs in heat exchangers and other chemical processing applications. There are many correlations for calculating drag coefficients since there are many configurations that the tubes can assume. So this slide has some examples of flow past spheres and cylinders. For the first example of this slide, you're given the temperature, diameter, pressure, and the velocity and asked for what the total drag force around the sphere is. You start this problem by going to Appendix A3 for air and getting the density and the viscosity off of this table. With the diameter, free stream velocity, density, and viscosity, you're able to calculate the Reynolds number. With the Reynolds number, you go back to the table or the graph that was on the last slide, figure 3.1-2, and you're able to get the drag coefficient off of it for a sphere, which is 0.47 in this case. After that, you can use all of the values that you just got and plug them into the total drag force equation to get 0.1958 newtons total drag force around the sphere. Your second example also gives the temperature, velocity, and diameter and asks for the force per unit meter. When you're calculating the force per unit meter, you assume that the length of the cylinder is 1 meter for the calculations. You then will use Appendix A2 to get the density and viscosity for water, which can be used to calculate the Reynolds number. Once you have the Reynolds number, you again go to figure 3.1-2 to find the drag coefficient for a cylinder to the corresponding Reynolds number, which is 1.4 in this case. You will then plug in the drag coefficients and the other given values to calculate your total drag force.
Okay, now moving on to flow and packed beds. I'm going to flow and packed beds. So spheres, cylinders, or irregular particles can all be packing material used in a packed bed. The void fraction, denoted as epsilon, is equal to the volume of the voids in the bed over the total volume. The specific surface of a particle is equal to the surface area over the volume, where a spherical particle has a specific surface equal to 6 over the diameter. And for a non-spherical particle, the effective particle diameter is equal to 6 divided by the specific surface. The ratio of total surface area to total volume of the bed is the specific surface over 1 minus epsilon, which equals to 6 times 1 minus epsilon over the effective particle diameter, with 1 minus epsilon being defined as the volume fraction of particles in the bed. Example 3.13 is the surface area in packed beds of cylinders. You're given the diameter, that is the length is equal to the diameter, and you're giving the density of the packed bed and the density of the cylinders. So part A is asking to find the void fraction, in which you divide the volume of the voids in the bed over the total volume. Part B is asking to find the effective particle diameter. Since the height is equal to the diameter, the volume and surface area can both be calculated, and substituting these values in the specific surface of a particle equation, which is the surface area over the volume, we can calculate the specific surface. And then lastly, substituting in the effective diameter equation, we can get that the effective diameter is 6 divided by the specific surface calculated previously. Part C is to find the total surface area to volume ratio. So you plug in the void fraction, which is part A, and the effective diameter, which is part B, to the total surface area to volume ratio equation to get A. Now we're going to go over how to calculate the pressure drop equation. So for the average interstitial velocity, which is denoted as V, is related to the superficial velocity, which is denoted as V prime, based on the cross section. So V prime is equal to epsilon times V. The hydraulic radius, which is denoted as RH, is epsilon over the specific surface, which is equal to the effective particle diameter over 6 times 1 minus epsilon. Since D is equal to 4RH, and using the average interstitial velocity relation, the Reynolds number for the packed bed is as shown. Combining the Hagen-Poiseuille equation and the hydraulic radius equation gives you an equation to solve for the pressure drop across the packed bed, which is shown. Okay, now for turbulent flow in packed beds. The same procedure for calculations in laminar flow is followed for turbulent flow in packed beds. This gives the pressure drop equation shown. Experimental data concluded that 3F is equal to 1.75. So for Reynolds number greater than 1,000, the Burke-Plummer equation can be used. Adding the equations for laminar and turbulent flow for low, intermediate, and high Reynolds numbers have been tested experimentally, giving the all Reynolds numbers pressure drop equation. This equation can also be written in terms of dimensionless groups. And for shape factor, this is for particles in packed beds that are irregular in shape. The sphericity shape factor, which is denoted as phi sub s of a particle, is the ratio of the surface area of the sphere that has the same volume as the particle you're measuring to the actual surface area of the particle, which is the surface area over the volume, and this volume is also the specific surface value. And for a sphere, 5 sub s is 1. And that's all.
Okay, so for mixtures of particles, this is for particles of various sizes, and the mean specific surface area is defined as the sum of the volume fraction times the surface area, where x sub I is the volume fraction. Combining the specific surface and mean specific surface equations, you get the effective mean diameter, which is just 6 divided by the mean specific surface area. The image shows an example of a mixture of particles of irregular shapes, and this example uses peanuts and Brazil nuts to show the difference between particle volumes. For example, 3.1-5, you're asked to find the mean diameter for a particle mixture, and you are given the volume fraction, diameter, and sphericity for all 3 particles, and you find that the mean diameter is 30 millimeters using that equation. So for Darcy's empirical law for laminar flow, this is for laminar flow in a packed bed. The flow rate is proportional to the pressure drop and inversely proportional to the viscosity and the length. And this is seen in the diagram and the equation that's found on the picture. V is the superficial velocity and is defined as the flow rate divided by the area. And the units of permeability, or K, are normally given in Darcy's or millidarcies. This equation has applications in measuring permeabilities of underground oil reservoirs. Next is flow in fluidized beds, minimum velocity and porosity for fluidization. When fluid at a low velocity flows upwards throughout a particle bed, the particles remain stationary. Once the force of the pressure drop times the cross-sectional area exceeds the gravitational force of the particles, they start to move. The minimum fluidization velocity, or V sub mf, is where fluidization begins. It's also the superficial velocity. The porosity of the bed when fluidization occurs is the minimum porosity for fluidization, or EMF. It is best to use gas as the fluid here rather than a liquid, since liquids give somewhat higher values of minimum porosity. The table to the left shows some typical values of porosity at minimum fluidization conditions. The pressure drop increases as the gas velocity increases until the onset of minimum fluidization. The volume is V equals 1, or length times the area, times 1 minus porosity, and is equal to the total volume of solids if they existed as one piece. You can also derive a ratio between multiple beds that gives you the length of one divided by the length of the other, where L1 is the height of the bed with porosity 1 and L2 is the height with porosity 2.
So as you know, a fluidized bed is a system in which solid particles are suspended in a flowing fluid, typically a gas or liquid, and exhibit fluid-like behavior. This suspension of particles is achieved by passing the fluid upward through a bed of solid particles at a velocity sufficient to counterbalance the weight of the particles. When fluidization occurs, the bed of the particles expands and the particles move more freely, resembling the properties of a fluid. Thus, the minimum fluidizing velocity is what induces the counterbalance on the particles, which causes the fluidization. And here on this slide, we can see that this is modeled by first looking at the approximate force in the first equation to start the fluidization pressure change multiplied by the area, which then can be further modified all the way onto the third equation, which is the Ergun equation. And this is where we can calculate the minimum fluidizing velocity. However, there are different cases, and on the next slide, we have the expansion of the fluidized beds. So there are 3 different cases. We have the small particles, and then fine solids and large solids. Now, here, this is in order to solve a problem using the previous slide's equations with the different cases, you must first identify the given parameters, such as the particle size, density, fluid density, viscosity, operating fluid velocity, and bed height. Next, you would determine the Reynolds number to choose an equation, such as the three cases here. And then the next step you would take is use the appropriate equation to calculate the porosity. And for example, with a small particle where the Reynolds number is less than 20, you would use an equation from one of Ella's slides where V prime is equal to K times the porosity cubed divided by 1 minus the porosity. Now, the next step you would take is analyze the limiting factors for the flow rate, such as the minimum fluidizing velocity and the entrainment of solids from the bed using the proper conditions depending on the Reynolds number range. And following those steps will get you the parameters you need, such as the porosity, bed height, and flow rate limitations. That concludes our presentation. Our references are on this slide, and thank you very much.